Okay, so let's watch a piece of a YouTube video in which we can actually see what it would be like to hear sound interference. This is the result. This is the result of having two speakers, which you can see in the video, and they're going to play this. They're playing this monotone, and you can well, they're measuring this sound with a microphone, but you can also, of course, hear it with your own ears. It's going to measure it first at the center, and then it's going to slowly move off center, and you'll hear the change. So the distance to the speakers is really not changing significantly, but if you like, the relative distance from the microphone to each speaker, that is changing and causing the sound to go through successive patterns of constructive and destructive interference. We can also get a visual of this by actually looking at that website, fet.colorado.edu, and see what it looks like when you have not sound waves but water waves interfering. So let me click on this. You can, of course, do this on your own. If you make one faucet go, it'll make drips at a certain rate, and then you can see the waves being produced. So the bright part is supposed to be like the peak in the wave, and the dark part is the trough. If I get both of them going, and the program will automatically sync them, give it a few seconds, what you'll notice is this pattern emerges because the waves sourced by each faucet are interfering with themselves. So what I want you to pay close attention to, in fact, let me point out that before I started this going, let me now reset this. You notice when the water level is sort of at normal equilibrium, it's sort of this gray-blue. When the height of the water is large, then it turns to bright blue. When the height of the water is low, it goes black. And so where it is okay, good, now they're both going. So you'll notice that as the pattern finally gets stabilized, you'll notice down the center you see successive bright fringes, they're called, or places where the amplitudes add up, because those are the places where there is constructive interference. It's either very large peaks or very low troughs. And you'll notice that happens other places as well. So like, for example, here you'll see it's bright, dark, bright, dark. But then there are places intermediate to the places who have constructive interference. In between, you'll notice that it's that sort of dull blue-gray kind of along this line here. That is a sort of line of constant destructive interference. You'll notice that pattern exists here and that pattern exists there. And again, this is what you're seeing as the interference of water waves, but it's the same math that goes into the interference of sound waves. You can imagine that if this represented sound waves and you were walking along from say, this part of the room to the bottom, you would notice that sort of there would be no sound over here. It would get louder, louder, and the loudest part of the sound would be in the middle, and then it would get weaker, 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 and then it would get louder and louder and louder. Okay, so we are talking about wave optics, and there should be some simulations or demonstrations that I've done. So something you may have noticed, and if you haven't noticed this in person, you can certainly tell from this aerial photograph of what happens when you have long wavelength waves of, let's say, ocean waves or bay, waves on a bay coming in towards the shore, as indicated by this long red arrow here. But if there is a breakwater, in other words, an obstacle that sort of blocks the path of the wave, what happens? And you might expect to see that wave kind of crash in the shore, continue on and crash into the shore, but then have a distinct line that distinguishes between where the breakwater was and where it wasn't. But as you can see, there's this nice sort of semicircular pattern where you're seeing waves that appear to have bent around that breakwater. And I guess the question is why, right? How is it that waves can bend around obstacles? This is totally at odds with the ray picture of light, and the ray picture of waves that have short wavelengths. So really the question is, how do waves bend around objects? How can we describe that? So before we get into that, let me see if I can draw a picture. So in order to try to understand this, we have to understand Huygens principle. Huygens, okay, I guess there was an S here. Huygens principle. Huygens principle and diffraction is what we are getting into now. So maybe we want to have some particular example in mind, like what happens when you take a pebble, you throw it into a lake, and you get these rippling waves that spread out. So for example, a pebble in lake, and it might start here, and then you get these water waves that start spreading outward. So you have like a nice peak here, and maybe there's a trough, and then later that thing has spread out, and that peak is now observed to be over here, and then there's a trough behind it. It's supposed to be the trough, and perhaps there's even another peak that was emitted later than that. And in case this perhaps is lost on you, the spatial separation between two successive peaks or two successive troughs, this distance should be the wavelength, or it is the wavelength. That's the definition of it. Okay, so what is going on here? So Huygens' perspective on this is that you can think of it, since the propagating wave is the result of a disturbance caused by the interactions of all the different pieces of medium kind of wiggling together, or some pieces causing wiggles in adjacent pieces. Huygens' idea was to think of each point along a propagating wave. So I'll put, I don't want to use that color, it's a different color. So for example, this point, this point, this point, this point, that really you can equivalently think of a propagating wave as the result of many, many points, in fact an infinite number of points on one wiggling part, as being the source of waves for the next. So if you imagine that, like, there's a little wave here, this, I'm going to zoom in on it. So one little source of wave making waves that kind of spread out in all different directions. Little source of wave here making waves that spread out in all different directions. This one, this one, this one. Lots and lots of little ones. Then at the next instant, the wave that you get will be the thing that sort of envelopes all of those different little waves, and that would be something that incorporated all of this. So it's one way to visualize how it is that a wave can not only spread out, but also how it can bend, if you think of it at each instant as being sourced by these little tiny sources of waves. These little things are called wavelets, and they add up to make the big wave. And so now let me zoom out and go back to this picture that is found in Giancoli. This is more or less saying the same thing. Huygens' principle, each point on a wave, the set of all points on the wave crest, the leading crest, the envelope that sort of captures all that stuff, that could be that is considered really the wave front. Okay, the set of all points that are expanding away from the source. Hopefully that makes some kind of sense. We're going to need this picture to understand how it is that waves can bend around obstacles. So since we're ultimately trying to go towards a description of light, let me remind you of something. That if we just think of light as a ray, then or let me back up a second. Suppose that there's a corner in your house. You've gone around the corner and you're standing here, and there's someone playing some noise. So like there's a speaker and it's making noise, or someone yelling, it doesn't matter. And the sound waves spread out, kind of like this. Why isn't it the case that the sound waves just kind of keep going like this and you don't hear anything? Instead, you'll notice that you can go around the corner and you do actually hear some noise, which means that, in some way, this isn't the right picture, these waves kind of keep going, keep going, keep going, get to the edge here, and then kind of spread out like this. How is it that waves can bend around the corner? And that can be understood in terms of these little wavelets. So sort of going back, do I want to draw the picture? I'm going to draw crappy pictures. You can imagine that at each point, there's little tiny sources of waves. Those waves propagate outward, and that results in a giant wave front. Keeps going, keeps going, keeps going, keeps going. You get to the end, and now you want to think about, all right, well, what are those little sources doing? Well, as they spread out uniformly in all directions, you get another wave front that's like this, and then, well, now you've got some here, and once they've cleared that obstacle, they can keep spreading, keep spreading, keep spreading. And I don't know if this picture is helping at all, but it's not like they're a bunch of particles that just carry momentum only going forward. They are the result, again, of the medium continually interacting with the adjacent particles. In this case, we're talking about sound waves, particles of air. And so that means that any disturbance here can be felt at a distance away. And let me now go to the other picture, which is hopefully better than this. So again, having in mind Huygens, what is it doing? You have a long wave. This would be considered a plane wave. It's the wave fronts are all parallel to each other and more or less lined up. They're going along, and then they reach an obstacle. And you'll notice, as the picture describes, the wave doesn't just propagate forward, but once it passes the obstacle, it starts to spread out. And that can be understood from this Huygens point of view. You'll notice that's true in A. It's also true in B. Notice that there is some bending that occurs, but towards the center of that propagation, the wave then more or less continues on like a plane wave. It's just kind of more confined. The smaller that opening, though, you'll notice that there's more obvious bending of the resulting wave front that comes out. That's the last picture I have here. Okay. Anyway, this effect, so now I'll just write this out in words. The result of waves bending around objects, is called diffraction. I'm gonna misspell it probably. And maybe we'll just sort of summarize the three words that all kind of sound familiar. I know that I sometimes struggle with vocab. Reflection is, what's another word for reflection? Basically think of this as light bouncing off of a surface. Light bounces off a surface or off an interface. That's probably a better way, more general way to say it. Refraction is what happens when light bends when passing through an interface. And fraction. And finally, diffraction is when light, or really any kind of wave, bends around objects.